PSNA College of Engineering and Technology presents online spoken faculty development program on advanced communication laboratory. Experiment number 2, session 2, mode characteristics of fibers, model MS Tester MCS04. This is our fiber optic cable section. So as you know that the fiber optic cable section is made up of the three structural regions. First one is the core. It is surrounded by the cladding and surrounded by the buffer region. As you know that the core takes the signal travel to proper reach the destination point. The surrounding cladding seems to be a protection layer for the signal travel. And last one is the buffer. It seems to be a secondary layer coverage for both core and cladding. In this structure you can able to see the second diagram or figure. It seems to be a signal travel, how the signal is taking over the core and how the signal is reflected and refracted over the cladding area. Although single mode fiber and multi-mode fiber cable are widely used in diverse applications, the problem about difference between the single mode fiber and multi-mode fiber is still confusing. Therefore, the following section will focus on the basic construction, fiber distance, cost, fiber color, etc. to make an in-depth comparison between single mode and multi-mode fiber. So these are the factors that are involving to classify the single mode fiber and multi-mode fiber. The first thing is the definition, second one dimension, third one transmission time and rate, fourth one attenuation or time to travel, fifth one merit, demerits, sixth one application, seventh one comparison, and last one types. And this is our first definition. The single mode fiber cable, due to small diametric core of 8 to 10 microns diameter, it allows only one mode of light to propagate through it. And multi-mode fiber cable, due to the large diametric core of about 62.5 microns diameter, which allows multiple simultaneous mode of light to propagate through it. And next section, optical fiber core diametric. In single mode optical fiber cable, core to cladding diameters is about 9 microns by 125 microns. In multi-mode optical fiber cable, core to cladding diameter is about 50 or 62.5 microns by 125 microns, which is depicted in the figures. And next section, transmission time and rate. Multi-mode optical fiber permits the signal transmission up to the distance of about 10 miles. Multi-mode fiber use cheaper optical transmitters or receivers. Single mode fiber converts distance greater than 10 miles. It uses costly laser diode as optical transmitters, and transmitted rate of single mode fiber is higher than the multi-mode fiber. It is also about 2 to 4 times costlier compared to the multi-mode version. And also we can discuss in the chapter of the transmission distance and rate. It is related with the wavelength and light source. Due to the large core size of multi-mode fibers, some low-cost light sources like LEDs, that is light emitting diodes, and VCSELs, that is vertical cavity surface emitting lasers, that works at the 850 nanometer and 1300 nanometer wavelength, are used in multi-mode fiber cables. While the single mode fiber cables often uses a laser or laser diode to produce light injected into the cable. And the commonly used single mode fiber wavelength is 1310 nanometer and 1550 nanometers. And the second region of coverage of this topic is the bandwidth. Multi-mode fiber bandwidth is limited by its light mode, and the maximum bandwidth at present is 28,000 megahertz per kilometer of OM5 fiber, while single mode fiber bandwidth is unlimited theoretically because it allows only one light mode to pass through at a time. And next section is the attenuation or time to travel. In a single mode fiber, due to the single core, the light reflection will be less and hence attenuation is lower, which makes light signal to reach faster. In a multimode fiber, due to the multiple cores, the light reflection will be more and hence attenuation is higher, which makes light signal to reach slower on the other end. But it can carry more data due to simultaneous transmission. And next, coverage of the merits and demerits. As mentioned, each has its own merits and demerits based on target application. The major demerit of the multimode optical fiber cable is that broadband RF signal cannot be propagated through it. And next we are going to view about the application in the first section. The section indicates how the multimode and single mode is classified into the two sectional area based on the low cost sources and low cost connection, that is the sources connections and installation cost and fiber cost and system cost and distance, etc. And the application side, it is mainly used for that is the case of multimode, it is mainly used for the LAN, SAN, data center, CO. In the case of single mode, it is mainly used for the application of WAN, MAN, access and campus. And this is the focus of the application in the second side. The single mode uses the backbone and distance of several thousands meters. For the multimode, it uses LED sources that generate difference angle along the cable, often used in LAN or small distance such as campus networks. And also the application view in broader way. Single mode fiber is used for long distance communication and for carrying very high bandwidth signal. The major application of single mode are CATV, telcos, universities as well as colleges. Laser diode is used as optical transmission system equipment here. Multimode fiber is used for short distance communication, mainly for video, audio, data-based wireless LAN application. LED-based fiber optic equipment is used for this. And this is in this section we are going to focus what is the major comparison between the single mode and multimode fiber are listed here. It is based on as usual, transmission equipment, cost of fiber, attenuation, transmission wavelength, application of the use, distance, bandwidth, advantage and disadvantage. And next we are going to see about the types of single mode and multimode fiber. The single mode fiber is classified into single step fiber and multimode is classified into the two types. The first one is the multimode step index fiber and multimode graded index fiber. So the first diagram indicates the multimode step index fiber, second diagram multimode graded index fiber and third diagram single mode step index fiber. So these are the things how the core is taking the signal is travel over the area of the propagation. So next we are going to detailedly study about how the single mode step index fiber is structured and what is the use of it. So we are going to see one by one. In the case of single mode step index fiber, light takes single path through the fiber core. Step index means sharp step in the index of refraction between core and cladding interface. This indicates that in step index, core and cladding have their own constant index of refractions, capital N1 and capital N2 respectively. The step index cable cross-sectional is depicted in this figure. So next we are going to analyze the multimode graded index fiber. In multimode graded index fiber, light follows multiple paths through the fiber core. In graded index of refraction is not constant but varies smoothly across the diameter of the core. Index of refraction is increased as one goes near the center while decreasing near outer core edges. Index of refraction is maximum at the center of the core. Induction of the refraction is constant for cladding part of the fiber. Based on the above, there are three types of the fiber optical cable is classified broadly. So next we are going to see about the what are the basic definition and computation of the numerical aperture is taken. We are going to study detailedly about the numerical aperture definition as numerical aperture of an optical fiber is the measure of its acceptance angle. So now we are going to define what is the meaning of acceptance angle. Acceptance angle is defined as the maximum angle at which the optical fiber accepts and transmits light through its core. The numerical aperture mathematical expression is given by NA N0 sin theta c, where N0 is equivalent to 1, that is the refractive index of air. Theta c is half the acceptance angle of the fiber. And numerical aperture, it is also elaborated into the one more mathematical expression, that is n core squared minus n cladding squared on the whole power of 1 divided by 2. N core and n cladding are the refractive indices of the fiber core and the fiber cladding. And another definition for the numerical aperture is how the light gathering in the fiber. The ability or capacity of the fiber gathering the light is also measured here. And the next slide, definition and computation of the V numbers and N. The definition of the V number is nothing but it is also called as the V number or cutoff frequency, which indicates the normalized frequency of the fibers. It is defined by the following formula: V is equivalent to 2 pi A divided by lambda in the numerical aperture. Kindly keep it in your mind, the V number formula, because this V number formula is calculated to analyze the single mode and multimode fiber cable in the upcoming sections. Where A is nothing but core radius and lambda is the wavelength of the light, and NA is nothing but numerical aperture, and N core and N cladding are the refractive index of the fiber core and fiber cladding respectively. So using the V number, you can give the conclusion for the how the guided modes are propagated in the fiber and how it is numbering it. For the step index fiber, the guided mode identified by the term of capital N, that is equivalent to V squared divided by 2. For a graded index fiber with a parabolic refractive index core profile, the guided mode identify the N is equivalent to V squared divided by 4. So next, if we are using the V number, you have to classify what is the meaning of single mode and what is the meaning of multimode. If V is less than 2.405 for a given wavelength, the fiber is said to be a single mode, and V is greater than 2.405 for a given wavelength, the fiber is said to be a multimode. How it is operated and details on all we can see in the upcoming section detailed using this experiment section. And this is our content of tester MCS04, which contains single mode, multi-mode, laser diode unit and detector screen. So these are the contents is basically used to construct this experiment. The first device will be the laser diode unit. The laser diode unit, this compresses a laser diode operating at 650 nanometer with a peak output power of 3 milliwatt. Optical power from the laser is coupled to the fiber through the ceramic 2.5 mm ferrule. The ferrule is the precision cylindrical ceramic part at the tip of the cable. Optical power coupled into the fiber may be adjusted by positioning the ferrule suitably, back or forth. Please note that cable connector fits into the notch provided on the laser diode unit. When the ferrule is fully inserted, rotating the ferrule will result in variation of the pattern observed on the display screen. The output power of the laser diode is settable through the potentiometer provided. One needs to set the laser output to the desired intensity. As the coupled power into the 9 divided by 125 single mode fiber will be very small, the lighting in the room may have to be dimmed to observe the pattern with clarity. On external 9 volt DC or 500 milliamp power supply is required to operate these devices. And second important devices is the detector screen. This compresses a fixed wide screen, 54 mm wide and holder on a solid metal frame. The position of the cable holder is settable at a fixed distance of 30, 45, 60, 75 and 90 mm from the screen. Two M3 screws facilitate mounting of the cable holder on the frame. The actual distance between the cable end and the screen need to be measured accurately. The cable holder has an SD adapter that provides for holding the cable in position. Provision is also made for an SMA cable adapter in one decides to study PMMA cables, SMA connectors too. Diameter of the light spots on the scale may be measured directly employing a suitable scale. Alternatively, the spot diameter may also be computed by capturing the image on a digital camera. The width of the screen 54 mm or any other marking on the screen also captured on the digital image will serve as a reference distance in computing the actual spot diameter. And the next section is the 1 ST 9 divided by 125 single mode step index fiber patch cord. And this is our single mode step index fiber, which is indicated by the color of yellow. And this is our specification of the 9 divided by 125 single mode step index glass fiber. So it is derived with the many number of the different parameters like numerical aperture, core diameter, cladding diameter, secondary coating, attenuation at the wavelength of 1310 nanometer and 1550 nanometer, effective group, refractive index, cutoff wavelength, mold field diameter for both wavelength, refractive index difference. So these are the values given for the single mode fiber cable. Similarly, we are going to analyze the 62.5 or 125 multi-mode graded index glass fiber patch cord, so which is indicated by the color of orange. And this is our specification of the 62.5 bore 125 multimode glass index fiber. So again we are going to classify or summarize the same kind of the parameter with respect to the single mode fiber to give the comparison. And this is our specification of the one more multimode graded index glass fiber, which is named by 50 divided by 125, which is optional for this experiment. So next we are going to see about the full setup to study single mode fiber characteristics. The complete experimental setup to study the mode characteristics of a single mode glass fiber is shown in this diagram. The single mode fiber is connected to the laser diode unit on the detector screen. Laser intensity is adjusted by setting the potentiometer. Power coupled into the fiber is set by adjusting the depth of the ferrule in the laser unit. Slight tilt of the ferrule may also be required for some cables. The pattern on the screen may be varied by gently distorting the cable in the midsection to change path length of the light propagating through the core. This has to be done carefully without disturbing the power coupling. The spot on the screen will be more distinct if the lights are dimmed in the laboratory. And this is our close view of the laser diode unit. How the fiber is connected with the laser diode unit, you can see here. This is our close-up view of the detector section. The black color indicates the numerical aperture ZIG. In the ZIG area only, the total number of the distance is separated, and here only we are fixing the one mount along with the connector of the fiber cable, and we have the one more screw at the detector screen. So these are the thing is viewed in the close-up. And this is our LP01 intensity pattern observed on the screen. So while we are doing this experiment, we are observing what is the light energy displayed on the screen. You can see the light intensity displayed on the screen. It is covered by the full circle. So you have to measure what is the diametric of that particular light energy to get the conclusion for the numerical aperture. The full circle, seems to be a light pattern. So it is named by the light pattern 01. And the second, after tuning occurred over the ferrule or midsection of the cable, you can observe what is the variation occurred over the screen. So it is named as the LP11. LP11 is nothing but light pattern 11. So it gives the significant difference between the previous pattern, that is LP01. The total circle is divided into the two regions, that is the semicircle. For the case of LP11, due to the variation occur in the ferrule and the midsection of the cable. So this is also the observation of the LP11. So how the two semiconductor is connected via the center. And this is our LP22 intensity pattern observed on the screen. Again we are making the disturbance over the ferrule of the cable and midsection of the cable. Again the total divided two section of the particular light intensity further is divided into the four section of the light intensity value. So it is named as the light pattern 22. So totally in the coverage of single mode area, after making the variation at the ferrule and midsection of the cable, we are covering the light intensity in the three pattern, that is LP01, LP11 and LP22. So this is our spotter. We are taking the example of any one light pattern. So the first LP01, it seems to be a clear view of the light pattern because it is the coverage of the full circle. So we are measuring the particular diameter for the calculation of numerical aperture. So 34 mm is called as the diameter of the light intensity. 166.5 mm. So here the line is marked in the horizontal. It is not indicating the width, it indicating the length of the screen fixed at the detector unit. And we have the actual width is measured over the scale on the screen is 54 mm. So now we are going to calculate the numerical aperture and V number in the next section. And this is our numerical aperture computation from the screenshot of single mode fiber spot. So numerical aperture of 9 divided by 125 single mode step index fiber is computed using the screenshot captured during the study of the pattern. So we are segregating into the number of steps. The first step will be open the screen image using the suitable software. We used Inkscape to measure the spot diameter in relation to the screen width. The actual screen width is 54 mm and the length of the screen is 166.5 mm. In the case shown below, that is the previous slide, the spot diameter is measured by the formula 34 cross 54 divided by 166.5. Here 34 indicates the light intensity, that is the diameter of the light intensity observed on the screen, and 54 is nothing but the total width of the screen, and 166.5 mm indicates the total length of the screen. So that is equivalent to 11.0 mm. So from that you can identify what is the spot radius. So the spot radius is nothing but the diameter divided by 2. So 11 mm divided by 2, that is equivalent to 11.0 mm divided by 2, that is equivalent to 5.5 mm. The second step will be the spacing between the fiber end and the screen is fixed at 50 mm. Now we are calculating the acceptance angle theta c is given by 2 tan inverse of 5.5 divided by 50. That is equivalent to 12.6 degrees. Here 5.5 is nothing but our spot radius and 50 is nothing but the distance from the screen to the mount which we are connecting the cable connector. And step 3, numerical aperture is given by sin theta c divided by 2, that is equivalent to 0.11. This matches the manufacturer's data. And last step is V and numerical aperture, not a numerical aperture, it is the guided mode and other parameter of the optical fiber cable may be calculated from using the manufacturer data and the numerical aperture obtained above. The wavelength of the fiber is 1260 mm and core radius is 4.15 microns. So these are the value which we are taking from the manufacturer data. So in the manufacturer data, core diameter only is given. We are taking the division with the 2 to get the core radius. So now we are going to calculate the V numbers. The V numbers is calculated based on the formula I already said, that is 2 pi a divided by lambda into numerical aperture. You have to put the 2 cross 3.14 instead of pi cross The radius will be 4.5 microns, that is 4.15 into 10 power minus 6, and divided by the wavelength will be 1260 nanometer, that is 1260 into 10 power minus 9 into numerical aperture is computed earlier, that is 0.11. So 2 pi a divided by lambda into numerical aperture, it provides the V number as 2.275. So now we are going to make the conclusion here is the V number of 2.275 is very less than compared to 2.405. So now we can identify that the mode fiber is single mode. So next we are going to see about the full setup to study the multimode graded index fiber characteristics. The complete experimental setup to study the mode characteristics of the multimode graded index glass fiber is shown in this diagram. The multimode graded index fiber is connected to the laser diode unit and the detector screen. Laser intensity is adjusted by setting the potentiometer. Power coupled into the fiber is set by adjusting the depth of the ferrule in the laser unit. Slight tilt of the ferrule may also be required for some cable. The pattern on the screen may be varied by gently distorting the cable in the midsection to change the path length of the light propagating through the core. This has to be done carefully without disturbing the power coupling. The spot on the screen will be more distinct if the lights are dimmed in the laboratory. This is our close view of the laser diode unit. So here the laser diode unit is connected with the cable section. So here we are using the multimode cable, which is indicated by the color of orange. And this is our close-up view of the detector screen diode unit section. So here the detector unit, I already said the detector unit is compressed by the two sections, that is the numerical aperture SIG. It is indicated by the bottom area of the detector unit, which contains the various level of the distance value in terms of millimeter, along with the one mount fixed with the cable area, that is the cable connector, that is called as the mount. And we have the one more section is the white color screen to observe the light intensity. And this is the intensity pattern observed on the screen. The first diagram indicates the intensity level observed in the dark mode, and second section the figure indicates the intensity diagram observed in the light mode. Again we are going to measure the numerical aperture similar to the single mode section. So here we are going to measure the numerical aperture measurement for the multimode section. So for the multimode section, again we have to analyze what is the spot diameter of the particular light, that is 116 mm, and what is the total length of the screen is 219 mm, and what is the actual width of the scale and the screen area is 54 mm. So now we are going to get the computation for the multimode numerical aperture section. So the heading is numerical aperture measured for the graded index multimode section. So here it is strongly indicated single mode. It is not a single mode, it is the multimode. And it is the computational steps followed to get the numerical aperture. Numerical aperture of the 62.5 divided by 125 multimode graded index fiber is computed using the screenshot captured during the study of the pattern. This method is described below. Step 1. Open the screen image using the suitable software. We used Inkscape to measure the spot diameter in relation to the screen width. The actual screen width is 54 mm in case shown in the diagram. The spot diameter is 116 into 54 divided by 219. 116 is nothing but the diameter of the light intensity displayed on the screen, and 54 is nothing but the total width of the screen, and 219 is nothing but the total length of the screen. So the total calculation providing the value of 28.6 mm. So this is the diameter of the spot. Now we are going to calculate the what is the spot radius of the light. So it is denoted by the 28.6 mm divided by 2, that is equivalent to 14.3 mm. The next step, we are going to calculate the acceptance angle. The spacing between the fiber and the screen is fixed at again 50 mm. Now we are calculating the acceptance angle theta c using the same formula. Only thing is we are replacing the what is the spot radius and the distance between the screen to the fiber end fixed at the mount of the detector unit. It is changed compared to the single mode, that is 14.3 divided by 50, that is equivalent to 32 degree. So using that, we are going to make the conclusion for the numerical aperture as sin theta c divided by 2, that is equivalent to 0.275. So now we are going to calculate the V number, the number of mode guided, and the other parameter of the optical fiber cable may be calculated from using the manufactured data, and the numerical aperture obtained above, that is in the manufactured data, are obtained by the calculation of the, that is sin theta c, not sin theta c divided by 2 mathematical expression. The wavelength of the fiber is 850 nanometer and core radius is 31.25 microns. Then the V number is calculated as is 63.69. So 850 nanometer which we are taking from the manufactured data sheet. Core radius also concluded from the core diameter of the manufactured data. Then we are as usual calculating the V number based on the formula of 2 pi a divided by lambda into numerical aperture. So 2 into 3.14 into a value was 31.25 into 10 power minus 6 and divided by 850 into 10 power minus 9 into the numerical aperture value is 0.275. After computation of these numerical values, you can get the full numerical values for the V number, that is equivalent to 63.69. So now we are going to give the conclusion for the multimode section is 63.69. It is our calculated V number, which is very greater than compared to our 2.405. Then the fiber is said to be a multimode. So thank you. So in this section, you can elaborately understood about the what is the basic thing behind the single mode and multimode, and how we are identifying the single mode and multimode cables using this experiment. So I thank the management of the PSNA CET, particularly in the EC department, to conduct this online spoken FTP program, and also I thank the Telenet system, MS equipment, and the faculty development program team for their entire support to proceed this event in the grand success. Thank you one and all watching this video.